Hello students, welcome to EPG Pathshala. I am Dr. Nasir Iqbal from Department of Physics, University of Kashmir, Srinagar. Today we are going to talk on the module The Variable Star Formation in the Universe under the paper of Astronomy and Astrophysics. After completing this module, the students will be able to Number 1. Learn basic processes which show how variable stars can be visualized and what are the different processes involved in the formation of these cosmic objects. Number 2. To know that there are many types of variable stars which can be categorized on the basis of their light emission. Number 3. To learn the concept involved in the formation of the variable stars. Number 4. Know that the observation of variable stars is strictly dependent on the total output of the light received from them. The possibility of explaining existence of the variable stars on the basis of the luminosity variation and the nature of different types of variable stars. So, to start with, the star formation has been and still continues to be an important aspect for explaining the evolution of the universe. The stability of the newborn stars depends on their gravitational behavior and their initial mass content. Those of the stars having large masses compared to our Sun have small chances of survival, whereas those stars having masses comparable to the mass of the Sun have more or less Sun-like life cycle. A star during its active phase never cools off due to the continuous nuclear reactions taking place in its core. These nuclear reactions change the lighter elements into the heavier ones, resulting in the light output in the form of luminosity, which we observe here on the surface of Earth. Hence, the star distribution in the observable universe becomes possible on the basis of the relationship between the luminosity and the spectral types. Here we have a relationship between the absolute magnitude and the spectral class of the stars. This relationship helps in developing a diagram which is properly known as Hertzsprung-Russell diagram, and it helps in tracing the stellar evolution in the most vivid manner. The diagram is here. Many of the observable stellar systems in the universe show variation in their luminosity with the passage of time. Such stellar distributions are said to consist of variable stars. If we go to a given diagram, which is called as the HR diagram, showing the characteristic features of all the known and observable stars in the universe. On the horizontal axis, we plot the spectral class of these stars, and in the vertical axis, we plot the absolute magnitude corresponding to the luminosity. So we have four important characteristics of the stars that are plotted in this HR diagram. We have the spectral class, we have the absolute magnitude, we have the luminosity, and we have the temperature. The absolute magnitude corresponds to the luminosity of the stars, and the spectral classification of the stars corresponds to the temperature of the stars. In the given HR diagram, we can see here we have few well-defined things like we have the white dwarfs, we have the main sequence, we have the giants, and we have the super giants. So there is an important thing how to look for this classification of the stars on the basis of this HR diagram. So we will talk here the general criteria for star formation. Formation of stars in the universe is a continuous process. The color magnitude diagram of the galactic clusters indicates that the star's formation takes place in the groups in the huge interstellar clouds. The diagram does not rule of the formation of the single star, but suggests a small but finite probability for the formation of the individual stars. In general, it is an established fact that the gravitational instability developed in the central region of the massive molecular clouds is the main cause of star formation. The gravitational instability breaks the original cloud into the fragments of different size containing a group of protostars in a diffuse gas envelope. The isothermal collapse generates a compressional heat which is subsequently lost in the form of infrared radiations. A very well-known person, very earlier, named as Sir James Jeans in 1920, developed a mathematical theory for the formation of the stars by treating different fragments of the interstellar clouds in static equilibrium. The criteria for static equilibrium condition has been taken as the V0 equivalent to 0, rho naught equivalent to constant, and P naught equivalent to constant, where the parameters V0, rho naught, and P naught are the initial velocity, density, and pressure of the cloud respectively. So, considering the cloud as a gravitationally bound fluid under small perturbation, the relevant field equations, which are a well-known equations, are defined here as dou rho 1 by dou t plus rho naught to delta dot v is equal to 0, which is the equation of continuity, and dou v1 by dou t equivalent to minus times 1 by rho naught delta times p1 minus delta times phi1, and delta square phi1 is equal to 4 pi g rho 1, and p1 is equal to the ratio between kt rho 1 and mu mh, which is written as c square s rho 1. Here in these equations, we have assumed that the gas is isothermal, with Cs being the isothermal speed of sound. All other symbols have their usual meanings. Above equations that we just described can be combined to derive the wave equation in the form as dou square rho 1 by dou t square is equivalent to rho naught c square s delta square rho 1 plus 4 pi g rho naught rho 1. So this equation, which is very important equation, it satisfies the plane wave equation whose solution is generally given by rho 1 is equivalent to c square s exponential of I times kx minus omega t, where k is the wave number and omega is the wave frequency. The perturbed wavelength is given by lambda is equal to 2 pi by k. From the above two equations, we can obtain the dispersion equation described by in the form of omega square is equal to c square s k square minus 4 pi g rho naught is equal to c square s times k square minus 4 pi g rho naught divided by c square s. Let us assume the factor 4 pi g rho naught divided by c square s to be equivalent to k square g. So the above equation will take the form as omega square is equal to c square s times k square minus k square j. One k is the small one and the other k is the capital letter. For negative omega square, the disturbance grows exponentially in time and the corresponding wavelength is called Jean's wavelength. It's defined by lambda j. J corresponds to the gene. So Jean's wavelength is equivalent to ratio of 2 pi by kj, which is also equivalent to square root of pi kt divided by mu mh g rho naught, where mh is the mass of the hydrogen, g is the gravitational constant. So once we substitute the numerical values of various physical constants in this very equation, we get the Jean's wavelength finally in a very simple form defined by lambda j is equivalent to 6 into 10 to the power 5 into square root of t divided by mu into rho naught and m. So the critical wavelength defined by this very equation suggests that the cloud of mass having dimensions larger than lambda j will be gravitationally unstable and will contract continuously under the gravitational pull. The corresponding critical mass, which is referred as the genus mass, is given by mj is equivalent to pi by 6 rho naught lambda cube j, which is equivalent to 10 to the power 21 into t by mu with the power of 3 by 2 rho naught with the power of minus 1 by 2 k into g. So it is in kg, means that it is in kilogram. As long as the isothermal state is maintained by the cloud of gas, it will suffer a continuous collapsing for the mass greater than Jean's mass. A very well-known Chandrasekhar and others. So Chandrasekhar was a well-known person. So Mr. Chandrasekhar and others, they collaborated and established that the forces other than the gravitational, such as arising out of the uniform rotation, turbulence and uniform magnetic field, cannot stop the collapse. For the uniform central temperature, means the isothermal condition, the collapse, called the free fall collapse, proceeds with resistance less acceleration. So let us consider a collapsing cloud to be spherically symmetric with a uniform density. The time required for a mass element of such a spherical cloud to reach from the surface to the center is known as the free fall time and is given by. So TFF means free fall time. So that is equivalent to 3 pi divided by 32 g into rho naught. So it is the square root of this factor 3 pi By 32 g rho naught, this time free fall time is measured in seconds, where, as already said, that rho naught is the initial matter density. The persistence of the free fall collapse will depend upon the time required for the heat of contraction due to gravitational compression to be radiated away. This time must be much shorter than the free fall time. The efficient cooling mechanism is due to the presence of dust grains and hydrogen molecules in the molecular clouds. So the dust grains, heated by the release of compressional energy, help the cloud to get cooled by radiating away the heat in the form of infrared wavelengths. Similarly, H2 means the hydrogen rotational levels are collisionally excited and downward transition radiates energy in infrared and other low frequency lines. The criteria for efficient cooling and free fall collapse in a standard molecular cloud is defined by the temperature approximately 250 Kelvin and the density rho approximately 10 to the power minus 23 and mu equivalent to 2.3. So, during several stages of collapse, strong central condensation in the density contribution takes place, followed by sharp shrinkage in size and mass of the central core, while the extensive outer region of the cloud is left behind, which collapses more slowly, having its size and mean density not much different from the initial values. The central density of the gas continues to increase till it attains the critical density of approximately the value 10 to the power 10 kg per meter cube, at which the opacity of the star starts building up in the cloud during the phase of its isothermal collapse. So the density distribution in the inner part of the falling cloud resembles that due to free fall, where the density rho is proportional to r to the power minus 3 by 2, while in the outer slowly collapsing region, the density law defined by the density rho proportional to r to the power minus 2 applies, resulting from the initial isothermal phase of the collapse. With the falling of the gas into the center, the outer region continues to expand over recovering the whole collapsing mass. With the onset of gravitational instability, fragmentation of the cloud commences that ultimately leads to the formation of subunits exactly as per genus criteria. As the collapsing cloud reach the critical density, the fragments start trapping the compressional heat, and thus the deviation from isothermal behavior begins. This stage is called the protostar formation stage, as shown here in the figure. The mass of the protostar can be as low as 2 into 10 to the power minus 3 solar mass at a temperature of approximately 10 Kelvin. The slow adiabatic contraction and gradual increase in density leads to increase in the opacity of a protostar that finally takes the protostar to the main sequence and a minimum mass of 8 into 10 to the power minus 2 solar mass. When we see this protostar formation, we can, in addition to our protostar formation, we have the disks produced and also a stream of high energetic charged particles which we called as the jets. So at this stage, the nuclear reaction begins to take place in a protostar, and within the free fall time of 10 to the power 5 years, the opacity is converted into transparency, giving rise to the formation of the first generation stars, preferably in groups with varying luminosity outputs. So, this description we can view from here in a given diagram where we have a mature group of variable stars. So, we talk about the energy and spectral distribution of variable stars. On magnitude scale, the pronounced variation of light is observed when the luminosity of stars begins to change, usually from 4 magnitudes onwards. The observed variation of light in long period variables, for instance, Mira variable is just 1 magnitude. The reason for this behavior is that the most of the energy of long period variables is in the infrared region owing to the low temperature of the star. So, this talks about the energy curve. Variation of light is roughly correlated with the length of the period. The greatest change in the brightness occurs in those stars which have exceptionally longest periods. On the other hand, the star on shorter periods have fairly symmetrical curves. The general inspection of the long period variable star, its spectra reveals that the spectral classification is cooler. 85% of these stars have M-type spectra with bright lines of hydrogen and few other elements. The remaining 15% have spectral classes R, N and S. The variation of the absorption spectra of variable stars follows the Cepheidis trend, that is hotter at the maximum light than at minimum. We talked just about the Mira variables. So, Mira variables, actually what are these? These Mira variables are some of the typical stars that show variation from M9 at minimum to M6 at maximum. The spectral type of long period variable stars are M, S, N with abundance of carbon and traces of SR, ZR, BA, LA, CA and TIO, MG, FE, etc. at low temperatures. Emission and absorption lines in long period variable stars, indicators of velocity curve variations. Bright lines are marked by the greater velocity of approach than dark lines in case of Mira variable stars. However, the smaller period variables have comparatively less approach velocity. At light maximum, in general, the velocity of approach shows a peak. Now, we talk about the characteristic features of these variable stars. Periods, spectral class, luminosity and populations are some of the important surveying parameters associated with all the variable stars. So we discuss these parameters here. As far as periods are concerned, their range varies from less than 2 hours for some RR lyric stars to almost 1000 days for some long period variables. The spectral class has a variation from bluish white to red. For example, Beta Canis majoris with spectral B has bluish white color. RR lyric stars with a spectral class range from A to F have moderately blue color. Long period variable stars have extreme red colors. And finally, semi-regular or irregular variables with spectral class range starting from K to M, K stars to M stars at an effective temperature of about 2 into 10 to the power 3 Kelvin have red color. The luminosity of variable stars is fairly high and extends over a range of 6 magnitudes or more. Population wise, the classical Cepheids and Beta Canis majoris belong to the population first stars. On the other hand, type second Cepheids, RR lyric stars, and RV Taurus belong to the population second stars. Long period variables, semi-regular and irregular variables lie in the domain between the two stellar systems. So, when we will talk about the observational analysis of variable stars, from the observational point of view, the observation of variable stars is an important component for their general categorization and characterization. The general catalogue of variable stars developed in 1958 by Soviet astronomers lists almost all observed variable stars on the basis of luminosity output. This catalogue lists a maximum number of long period stars. So about 3657, followed by Cepheids about 600, followed by Eugeminorium about 112, followed by RV Tauri about 92, and others like Beta Canis majoris, RR lyric, etc., red irregular, semi-regular, and flare stars are some other variable stars which have been observed experimentally by several workers on the basis of emission and or absorption spectral line. Theory for variable star formation in reference to the pulsation and astroseismological mechanism. The actual case of the observed light and velocity variation of the intrinsic variable stars was first proposed by a German physicist, namely A. Ritter, in 1879. Consider a star of density ρ performing adiabatic radial pulsations in a period say Tp. So it has been found that the pulsation period Tp is given by the relation like square root of 3 pi divided by 3 gamma minus 4 into 0. So this relation is important in the sense that we can calculate the pulsation period of these variable stars. If we take ρ as the density rather as the average density of a real star, then the application of equation can be extended to all variable stars. In 1940, H. Shapley's investigation into the nature of variable stars proved that these stars undergo astroseismological radial pulsations, thus rejecting thereby the binary hypothesis. Shapley's idea, coupled with equations 13 and 14 by Ritter, were later confirmed by Sir Eddington. However, in view of the overwhelming abundance of hydrogen in the stellar material, if we take this common to be taken as 5 by 3, the computed periods with Eddington's formula fall short of the observed periods, subject to the condition that normal man-secant stellar density is adopted. This led Eddington to the conclusion that the density in Cepheids must be very much less compared to that of the man-secant stars. The most satisfactory explanation about the true nature of the pulsation that properly takes into account the observed phenomena of Cepheid variation came from Martin Schwarzschild in 1938. He suggested that it is only the interior core of the star that pulsates and sends compressional waves to the photospheric layers of the stars. According to this model, the maximum brightness occurs when the speed of the compressional waves is highest one. The observation compares well with the light curve and velocity curve relations. The modified pulsation hypothesis ultimately emerged as the only acceptable explanation, which is harmony with the observed Cepheid phenomena. Pulsation theory and spectroscopic analysis of variable stellar systems have been extremely helpful in understanding the Cepheid phenomena, but the physical cause of pulsations is still not properly understood. One of the possible physical causes for the generation of pulses has been attributed to the criteria of the critical hydrogen correspond to the helium ionization zones around the star envelope that initiates and maintains the mechanical oscillations. The theory was put forward by a Russian astrophysicist, namely S.A. Zivaskin, and is yet to be confirmed by more independent ways. So students, let us see what we are going to learn in this module. The main aim of this lecture has been to define a variable star in terms of its apparent change in the brightness with the passage of time. We have remained focused with the intrinsic pulsating variables in which changes of luminosity are mostly regular and periodic. The categorization of the variable stars has been done on the basis of the length of their periods, the nature of variation of their light, and their spectral characteristics. Thank you.